Hi, in this part of the lecture, we are going to talk about an example of regenerative Rankine cycle. In this example, we are going to consider an ideal regenerative Rankine cycle. The steam that entered the turbine would be at the condition of 3 megapascal and 500 degrees Celsius. And the final exhaust pressure would be at 10 kilopascal. In this Rankine cycle, we are going to use a single open feed water heater. Which operates at 0.5 megapascal. So you can see that in this Rankine cycle, we are operating with 3 different pressure levels. The highest pressure would be at 3 megapascal. The intermediate pressure would be at 0.5 megapascal, and the lowest pressure would be at 10 kilopascal. Okay. Now in this example, some information are already provided. Okay, you can see that we have information at some point number 5, number 6, and number 7, which is related to the turbine condition. Okay, so number 5 would be at inlet. Okay, number 6 would be at the extracted point, and number 7 would be at the turbine outlet. Okay, all right then. We also have some useful information at the saturated condition as follow here at 10 kilopascal, 500 kilopascal, and 3000 kilopascal. All right. Now let's have a look at the cycle on the TS diagram. Okay. On the TS diagram, you can see that we are going to operate this cycle on 3 different pressure levels. We have high pressure, we have intermediate pressure, and we have low pressure here. Okay, you can see from the information in the previous slide that information at number 5, number 6, and number 7 are provided. Okay, you know enthalpy H5, H6, and H7. Okay. Apart from that, because this is ideal Rankine cycle, so it means that the condition here at number 1 and number 3 here would be sat liquid. Sat liquid here. Number 1 is also sat liquid as well. So you know both pressure, you know P1 and you know P3. So number 1 and number 3 are fully defined. You can use the steam table, okay, to determine the enthalpy at point number 1 and point number 3. So it means that you have number 2 and number 4 remaining to be considered or to be calculated. Okay, number 2 and number 4. You have to calculate enthalpy at number 2 and enthalpy at number 4 here. Okay. Since this is the regenerative Rankine cycle using an open feed water heater, so you can see that the flow rate at any particular point will not be equal or will not be constant. Okay. In this case, you can see that we have the boiler from 4 to 5. Okay, 4 to 5 here. The flow rate would be in the full fraction of 1. Okay, the first part expansion, the flow rate is also 1. Second part expansion, flow rate would be 1 minus y. Okay, the extracted amount would be y here. Extracted amount is y here. Okay, the flow rate through the condenser from 7 to 1 would be 1 minus y. Okay, 1 minus y. And we have to pump the liquid condensate from 1 to 2. Okay, we mix 2 with 6 to obtain 3, like this. Okay, and we pump 3 to 4 in the second pump, like this. Okay, now I can write the mass flow rate at any particular point as a function of the mass flow rate at the turbine inlet. Okay, so I will have m1 dot, okay, equal to 1 minus y m5. Okay, it's according to the fraction, okay, that we have in the diagram. M2 would be the same, would be equal to 1 minus y m5 as well. Okay, M3 here would be equal to M5. It became full fraction now. M4 is also equal to M5. Okay, M6 is the mass flow rate that we withdraw at intermediate pressure from the extraction turbine. M6 would be equal to y M5. Okay, M7, lastly, M7 would be equal to 1 minus y M5. So you can actually write the mass flow rate at every point as a function of M5. This would be very useful when you write the energy balance, okay, to do your calculations. Okay, now let's move on. We have to consider process in the first pump. Okay, in the first pump, we can estimate the power that we need for the first pump. Okay, so for the first pump, we can estimate the work required by calculating by the V1 multiplied by P2 minus P1. Because it's the incompressible liquid, you can estimate the work from specific volume multiplied by pressure change. Okay, so in the first pump, we increase the pressure from 10 kilopascal, the low pressure value, to 500 kilopascal, which is the intermediate pressure value. Okay, so the work required for the first pump would be just 0.5 kilojoule per kilogram, very small one. Okay, for the first pump. We can then calculate enthalpy at point number 2 by doing the energy balance around the first pump. So H2 will be equal to W pump 1 plus H1. So that would be 192.3 kilojoule per kilogram. So point number 2 is now fully defined now because you know the enthalpy value. Okay, now moving to point number 3. Point number 3, although you know the enthalpy, but the other parameter that you need to know, and it's very important, is the fraction of the steam that you have to extract from the extraction turbine, or the Y fraction value. The Y fraction value, you can do that, you can calculate that by doing the energy balance, okay, around the open feed water heater. So you have the open feed water heater. Okay, you have the steam that you extract from the turbine at number 6. You have to mix it with liquid from the first pump, which is number 2, and you will get number 3. Okay, you get number 3 here. So from the mass and energy balance around the open feed water heater, you can calculate the fraction that you need to extract from the turbine. Y here, you can calculate it from H3 minus H2 divided by H6 minus H2. So you know all the enthalpy value. H3 here is the sad liquid at intermediate pressure. H2 here, this one you have just calculated from the previous slide. And H6 is already provided by the problems. Okay. So the result, it would be 0.163. Sorry, 0.163. So this is a fraction. So it means that from the turbine, okay, inlet at number 5, okay, you extract out at number 6, okay, and the final exhaust would be at number 7. With the full fraction entering at number 5, you will extract with the fraction of 0.163. And the remaining will go out at the final exhaust, okay, number 7, which is the fraction of 0.837. This is a fraction of the steam coming out at the final exhaust. Okay, so you have the fraction at each point like this. Now we move on to calculate the enthalpy at point number 4. Okay, we can do the same thing with the pump number 1. We can estimate the work required for the second pump, okay, by calculating from the specific volume multiplied by P4 minus P3. Okay, so in this pump, it will increase the pressure from intermediate pressure to the highest pressure, 500 to 3000 kilopascal. The work required for this pump would be 2.7 kilojoule per kilogram. Okay. Now once you have the work required for the second pump, you can do the energy balance around the second pump to determine the enthalpy at point number 4. Okay, so H4 would be 642.8 kilojoule per kilogram. Now, to calculate the thermal efficiency, we need to determine the net work output, and also we need to determine the heat input required. Okay, now let's calculate the work that we would obtain from the turbine first. From the turbine, okay, you can see that this turbine is special. It's not like the turbine that we have considered before, because it's an extraction turbine. It has one inlet, but it has two outlets, one at intermediate pressure and the other at the lowest pressure here. We have inlet at number 5, we have outlet at number 6 and number 7. Okay, so the mass flow rate coming in would be M5. Okay, the mass flow rate at the intermediate point would be YM5. The mass flow rate coming out at the final exhaust would be 1 minus YM5. Okay, we can do the energy balance. Energy flowing in will be equal to energy flowing out. We also have another energy flowing out, that is the turbine work. Okay, turbine work, W turbine work here. So we can write the energy balance. Okay, now to write the energy balance here, you have to write it in the rate form. The rate form means that the form that is the heat rate or the power rate. Okay, heat rate or power rate. So you have energy in would be M5 H5 equal to energy out, that would be W turbine, W dot here, okay, plus M6 H6 plus M7 H7. Okay, you can see that the reason why we have to write our energy balance in the rate form is because the mass flow rate at the inlet point and at each outlet point are not equal. Okay, so in this case we can write M6 in terms of M5, we can write M7 in terms of M5. Okay, as I have written here, M6 equal to y M5, M7 equal to 1 minus y M5. Okay, now we can rewrite this equation to calculate the turbine work. Okay, in this case, we don't have the flow rate, total flow of the steam inside our cycle, so we can divide M5 on both sides. Okay, so we will get the turbine work, the specific turbine work, equal to H5 minus YH6 minus 1 minus YH7. Okay, since you know every value, H5, H6, H7, and also the Y fraction you have just calculated from the previous slide, you can substitute all the values to calculate the turbine work. Okay, so you get the turbine work here, 1058.6 kilojoule per kilogram. Now you can calculate W net. W net will be equal to W turbine minus W required for the first pump minus W required for the second pump. Similar to the previous energy balance that I have mentioned before, you have to write it in the rate form, W dot, like this. Okay, because of the mass flow rate through each equipment are not equal. Okay, so W net here will be equal to M5 multiplied by small W net. Okay, equal to M5 multiplied by W turbine minus M1 multiplied by W pump 1 minus M3 multiplied by W pump 2. Okay, you already know that you can write M1 and M3 as a function of M5. M3 here is also written as a function of M5. Okay, so once you have written all the terms, okay, in terms of M5, you can cancel them out. Okay, M5 will disappear. Okay, and W net will be just W turbine minus 1 minus Y W pump 1 minus W pump 2. And you know everything. You knew the turbine work, you knew the pump work for the first pump, you knew the pump work required for the second pump. So the result, W net would be 1055.8 kilojoule per kilogram. You get W net now. The next thing that you have to calculate would be Q in. Okay, you can calculate the heat required in the boiler by doing the energy balance around the boiler. Okay, so Q in would be equal to H5 minus H4. Okay, you know H5 and H4 already. You can substitute them to determine Q in. So Q in would be 2814.8 kilojoule per kilogram. This is your Q in. The thermal efficiency of this regenerative Rankine cycle can then be calculated by W net divided by Q in, and that would be around 37.5%. Now if you compare the result of the thermal efficiency with the Rankine cycle without any regeneration, the thermal efficiency of that simple cycle is just 35.6%. You can see that with the regeneration, you can improve the efficiency by 5.3%. Okay, when compared to the original one, or it would be improved by around 2 percentage point. 2 percentage point. Okay, 37.5 minus 35.6. Okay, that would be around 1.9%, around 2%, 2 percentage point increase. Okay, that is quite a lot for the power cycle or the steam cycle. But you improve efficiency with the sacrifice in the network output. The network output would be reduced because you extract some amount of steam for the regenerative scheme. So the power that you would get from the turbine would be reduced. The network output for the regenerative cycle here would be about 10% lower than the standard Rankine cycle. So this is the price that you have to pay for. Okay, you get improved in terms of efficiency, but you get less network output. Okay, in this case. All right then. Now, someone might be wondering, what should be the pressure, the intermediate pressure that we should operate? Okay, what is the intermediate pressure that we should operate? The pressure of the OFWH pressure, POFWH here. This is the intermediate pressure in our regenerative cycle. Okay, what should be the intermediate pressure that we should operate? Okay, now let's take a look at this graph here, this relationship here. You can see that if you start from a very low value of POFWH or low value of intermediate pressure, okay, you can see that at low value of the POFWH, okay, it means that you extract the steam at low pressure, or you extract the steam at the point which is close to the exhaust point. Okay, so P6 is low. P6 is low. Okay, so it means that when you extract the steam at low pressure, the temperature of the steam here would be low as well. So you can increase the temperature of the water just not much. Okay, so T3 here is also low as well. Okay, so the effect here, if you operate at low POFWH, you find out that here at this condition, the latent heat of the steam at low pressure would be high latent heat. Okay, high latent heat, and you can just increase the preheating temperature just a very small level. Okay, T3 is very small. Okay, so the amount of the steam that you need would be small as well. So it means that Y here, or the amount of extract steam that you need at this condition would be small. Okay, now if you increase the intermediate pressure, if you increase the POFWH further, okay, if you increase it to like a high value like this one, this is the high POFWH, okay, and you can see that the temperature of the water that you can increase would be higher. T3 would be higher. Okay, higher here. T6 is also high as well. Okay, so it means that if you operate at high POFWH, okay, you find out that you need to preheat the water to a higher temperature. T3 would be at a higher temperature. It means that you have to extract more steam. You have to extract more steam. Large amount of steam must be extracted, or Y would be increased. You have to extract more steam. And at this high pressure condition, you find out as well from your steam table that the latent heat is also low. With low latent heat, with high preheat temperature required, it means you need more steam to be extracted at number 6. So you can see that here, as you increase the POFWH, you have to extract more steam. As you extract more steam, what happened to the work would be you will get less net work output. The work that you get from turbine would be reduced. Okay, so you can see that it's not quite the effect that we are looking for. If you operate at high pressure, you extract more steam, you get less work. Okay, extract more steam, Y increase, but work decrease. Okay, so what would be the best value of the POFWH then? What is the value which is the best value for POFWH? So we have to look in terms of the cycle efficiency. Okay. Now if you plot the cycle efficiency with the POFWH, you find out that the curve will exhibit a maximum point, okay, at some pressure value. Here in this case, it would be around 400 kilopascal. So it means that we should actually use the intermediate pressure or POFWH at around 400 kilopascal. That would be the best because you will get the maximum thermal efficiency. But why does the curve looks like this? Why do we have increase in the thermal efficiency at the beginning, and then why do we have a decrease in the thermal efficiency later on after we increase from 400 kilopascal further? Okay, I will explain the reason here by using the same graph again. Now you can see that with the cycle operating at low POFWH, low pressure here, low intermediate pressure here, you can see that the amount of net work lost, is smaller than the benefit that you would get from the saving in Qin. Okay, so the saving in the heat input is what we are looking for. This is the positive effect. The loss in W net is the negative effect. Okay, in this region here, when the intermediate pressure is lower than 400 kilopascal, the effect of saving in the Qin is greater than the loss in W net. So in this region, you find out that when you increase the pressure of OFWH, you get increase in the thermal efficiency. Thermal efficiency will be increased because the benefit is greater than the disadvantage or the loss that you have to pay in terms of W net. Now, once you have reached the maximum point and you keep increasing the pressure further, you find out that the effect of the loss would be greater now. The loss in W net would be greater because in this region here at high pressure, Y value would be very high. You have to extract large amount of steam. So the effect of the loss in W net would be far greater than the saving that you would achieve in the Qin. So in this region, you find out that the thermal efficiency will decrease if you further increase the pressure. Okay, so from the result here, you should operate the OFWH pressure at the optimum point, or the point which can give you the maximum thermal efficiency. Okay, not just any value, not just any pressure. You should find this optimum pressure here and operate at that pressure. Okay, so you can see that the regenerative Rankine cycle can give you the benefit in terms of the efficiency, okay, increase in efficiency, but not in terms of the network output, because the network output would be lower. Okay, all right then. That should be all for this example. Thank you.